Hi, my name is Mia Chiquier, and I'll be presenting our work, Muscles in Action. Human motion is created by, and constrained by, our muscles. However, the majority of computer vision systems today only model motion by tracking the surface of the human body. We take a first step at building computer vision methods that represent the internal muscle activity that causes motion. To achieve this, we leverage a sensor called surface electromyography. This sensor captures the potential difference of the electrical signal that is sent from your brain to contract your muscles. We put 8 sensors on both biceps, both quadriceps, both laterals, and both hamstrings. Next, we needed to construct a dataset. This is not the first dataset of its kind. To provide some historical context, in the 1960s and the 1970s, 2 researchers named De Luca and Basmadjian started a wave of EMG dataset collection and understanding. While many studies on EMG were performed during this time, most of these datasets were small and did not include video. We present a new and large standardized dataset, Muscles in Action, that contains paired EMG and video to learn to incorporate muscle activity into human motion representations. The Muscles in Action dataset consists of 12.5 hours of synchronized video and SEMG signals for 8 muscles across 10 subjects. The dataset consists of 15 exercises shown below. Each subject performed each exercise for 5 minutes, and we asked them to vary the execution speed, effort, and orientation. Next, using this dataset, we build a motion-to-muscle encoder, which learns to regress SEMG values from video. As a pre-processing step, we extracted 3D key points using Vibe, and then use a transformer to regress the values. Similarly, for the muscle-to-motion decoder, the input is the surface EMG values, and it learns to regress the 3D key points over time. Here is a qualitative example of our muscle-to-motion encoder. The dashed line is the ground truth and the solid line is our prediction, which follows the ground truth closely. We adjusted the scale of the axis to fit the range of the ground truth muscle activation. Next, here's a qualitative example of our decoder. The green is the prediction and red is the ground truth, and we see that both follow closely. As for some quantitative results, in Table 1, we report the mean squared error on predicted EMG from our encoder in Table 1. We observe that for all of the 15 exercises, both our conditional and non-conditional models outperform both conditional and non-conditional retrieval baselines. Conditioning in this case refers to conditioning on the subject. For the out-of-distribution experiments, we retrained 15 models on 15 different datasets, each dataset leaving out one exercise. For each model, we then ran inference on the exercise that was left out and reported it in the last 4 columns of Table 1. The results indicate that our learning method generalizes better to unseen exercises than the retrieval baselines. As for the decoder, we report the root mean squared error per exercise for both the conditional decoder and non-conditional decoder in the Table 2 on the right here. For all of the 15 exercises, both our conditional and non-conditional models outperform both conditional and non-conditional retrieval baselines. Now for the exciting bit. We show how examples of the motion muscle mappings can be leveraged to generate motion recommendations subject to muscle constraints. We predict the muscle activation for a given motion, and then we modify one of the muscle predictions by scaling it either upwards or downwards before decoding back into motion. This creates a new quote-unquote recommended motion that respects particular muscle group goals, and we call this form of editing muscle scaling. Here are some accompanying videos to demonstrate the results. The first video has a squat as the motion input. We first use our encoder to predict the muscle activations for each muscle, and then we scale the predicted hamstring and lateral activations with a scalar greater than 1 before decoding to motion. We notice that the recommended motion is similar to the input motion except that the feet are wider apart, thus further engaging the hamstrings. The second kind of muscle conditioned motion editing that we show is what we call muscle stitching, a reference to the classic computer vision problem of image stitching. Given an input motion, we predict the muscle activation, and we replace the prediction for a particular muscle group with the predicted muscle activation for an entirely different motion. This hybrid muscle activation has never been seen before in the training set, yet the decoded motion corresponds to the hybrid motions correctly. These results illustrate our model's emergent compositional capabilities. The first video has a front punch as the motion input, but we replace the predicted hamstring muscle activation with a hamstring prediction for a back kick, and we see that it generates the correct hybrid motion. Thank you for listening to our presentation, and please check out our website, musclesinaction.cs.columbia.edu for more examples and explanation.